For such difference of surds, what we usually do is to deal with the conjugate, right? The radical conjugate. So what I'm going to multiply here is what is it? Of the same kind, but with the opposite sign, right? Plus is going to then make it better. But then, we need to do top and bottom on both of them so that we're essentially multiplying by 1, isn't it? Right? If that happened, then it's going to be limit n goes to infinity. And on the top, man, it's a plus b times a minus b, hence the difference of the square, n plus 1 minus n minus 1 over, and voila, is going to be the sum of the surge. And hence, on the top, it's going to be n goes to infinity, 2 over whatever. And if you look at him, if you say n to infinity, this is infinite plus infinite n. Should you not be confused, this is not indeterminate form. Infinity minus infinity will be divergence, which is a large number, right? However, if it was infinity minus infinity, that is indeterminate, right? We shouldn't be confused with this. Hence, is a constant over infinity. That will imply that it's going to be 0. Okay, so whenever we have this type of the conjugate case, please make sure you're able to make it into the the quotient. All right, so that's how we're going to make it quotient, by multiplying the difference of the square. Hence, we get the 2 over infinity. So far, so good. And I will leave it as an exercise. And but this is a quotient form also. And if I said infinity, the top is going to be infinite, the bottom is also infinity. Hence, we have indeterminate form, right? Hence, we have indeterminate form. But then, what do I need to multiply? How do I simplify? Will be left as an exercise. Okay, but here's the thing. I get it. I get the quotient form so far with the polynomial forms was straightforward, right? But then when I look at this, it's sort of a different quotient now because I've got the sign on the top. I've got the sign on the top. So even if I divide by the n on each top and bottom, I don't know what it means, right? For him, we can't do the algebra of limit now. So we need to introduce the second technique, something called the squeeze theorem, right? We're going to work now with the second technique of finding the limit called the squeeze theorem. So this is the statement, but let me try to show you the visualization. Is that following? You see, when I think it might be too bright for you guys, but if I get the picture here, suppose I have a upper bound of a certain sequence as the following. Suppose this is a Cn, and suppose that my Bn is like that, and whatever in between An. So let me use a different color. Even if it behaves crazily, it's okay. It is going to, in fact, converge to the same limit. So suppose I have the following inequality as An, Bn, and Cn. Boom, boom, right? It's bounded. However, if they converge to the equal limit, upper and lower bounds, then the An also needs to converge by the squeeze theorem. Okay? You don't need to prove it. Proving will be happening in college. Right? So that's the visualization of the behavior of the squeeze theorem. Let's have a look at that. Try to use the squeeze theorem on him. But here's the thing. For squeeze theorem, you need to then be very aware about the bounds, right? We need to be aware about the bounds. And if you look at the sign, he's bounded by +1 and -1, right? And hence, since sign is bounded, then I can easily find the lower bound and upper bound of the such sequence, right? So -1 over n and 1 over n. And if you set n to infinity on both of them, it becomes a 0 as well as a him, right? Therefore, whatever in the middle also should go to 0 because left and right goes to 0, right? So it is very important for me to know what bounds I'm going to set up for my sequence. So, on the YouTube chat, I want you to tell me what bound I'm going to choose for the arctangent of n squared. What bounds would you like to put for the arctangent n squared? What bounds would you like to put on arc of a square? Is my numerator bounded? I think so. And if so, it's bounded by who? Thank you, right? It's a plus minus pi over 2, right? It is bounded by plus minus pi over 2. Therefore, my sequence here, you know, the denominator, I leave it alone. But it will be bounded by plus minus pi over 2, you see? And then if I send n to infinity, this will become each of them 0, right? Therefore, the sequence of that will be also 0. So it is very important when I see something of a trick like sine, cosine, or inverse trick, that I should be very confident being able to derive the squeeze theorem. But here's the thing. Here's the thing, you know, sometimes it's not straightforward. Sometimes it's not straightforward to find the inequality. The upper bound and lower bound. And for that, what the exam questions do, they give you the inequality to prove. Okay, they give you the inequality to prove. But here's this. How do I prove the inequality? Especially we are dealing with the sequence and series, isn't it? And look, my n is bigger than equal to 6. My n is bigger than equal to 6. And sequence is discrete, hence we're dealing with the positive integer, you see? If I'm dealing with the positive integer and I'm proving a statement, what we use is the induction, right? What we're going to do is to use induction. So hence, proving inequality requires induction. Okay, it's a natural number, and every time we always have to come up with the proof by induction. So I will leave it as an exercise for you to prove this using induction. If you get stuck, no problem. Ask me. During the question time, I'll gladly answer your induction problem as well. But solving inequality, in order to apply for the squeeze theorem, requires a use of the induction. Okay, and suppose you did that, right? Suppose you proved this inequality. And here's the thing, you know, I wanted to find the limit of this quotient, right? 6 to the power of n over n factorial. But what I realized is that according to the inequality that you are supposed to have proved using the induction, is upper bounded by 6 to the power 5 over 5 factorial times 6 over n. And then since we're talking about the positive integer, it is also bigger than 0. So what I need to show that if I could let the upper bound converging to 0 by the squeeze theorem, the one in the middle is going to go 0. But it is, right? Because these are constant, no matter how big that number is, don't matter, right? Because divergence is going to win for the denominator, right? Hence, by the squeeze theorem, it is also therefore going to go to 0. Okay. And you know, also inequality, my friend, and then they are asking for n in positive integer. They don't mention proof by induction, but you need to show by induction. Okay, you need to show by induction. But for this one, it's not quite nice. So I'm gonna actually prove it together. Okay, so I'm gonna go with. Okay.